All right, so welcome. The question for today's video and our first lab is, do you suffer from hydrophobia? Like our pufferfish or cats? Gnomes definitely do not. And so the lab one is the myth of the universal solvent. This is actually a slideshow I made originally 4 years ago. I teach for 10 years, 11 years now, to homeschool middle schoolers. And so Kaylee was in my class like 5 years ago. And Kaylee, you are saved on this one because since I'm at my mom's, all the pictures I have of you from 5 years ago are on my other computer. I thought I'd save them on this one. And so we don't get a guest appearance picture from Kaylee. All right, so let's see where we're going to go with this. So you guys all know this, how much the Earth's surface is water, right? I'm pretty sure you all know the answer, which is definitely not 100% because we're not in Atlantis, but it's around 71-ish%. And so then this is the cool part, is how much of the human body is water. Well, in you and me, it's the same answer. This is really cool. I found this online. So we're going to assume you're all normal adults, that we're about 71% water, the same as this beautiful planet. And, if you want to go back to the origins of our planet was more water at one point. And as land has formed. And let's move on. So water in our body does so many different things. This is actually a pretty fascinating question, and I'm sorry that we can't be live recording this because this would be an awesome bonus question. It's obviously not our bones. Our bones, right, are earth, so they're made up of minerals. And our brain, well, yeah, it's pretty solid too. Heart, muscles, oh, kidneys. That would be a good answer. About our skin. This is actually what people do to have better skin. So there's hyaluronic acid is the slime of slugs and snails. And it's actually what baby skin has high levels of hyaluronic acid. So most skincare products now have hyaluronic acid because it moisturizes your skin. And so, you guys are all going to be picking a topic at some point. This is a fun topic, and I'll even give you bonus points if you do your whole presentation with snails on your face or slugs. I've yet to do it, or I could be right now. So there you go. Yeah, blood, kidneys, liver. Always forget about the liver. Liver is so wonderful. We should all send love all the time to our liver. But it turns out none of those are the answer. Of course, our eyes are actually 95% water. All right, just a fun fact. Nothing you need to take notes on. This is more to prepare us for what you're going to be doing in the lab and things that we'll be talking about as the term goes on. So water is the most ordinary molecule of life. We kind of take advantage. We just take it for granted, right? We take beautiful pictures of the sunset, and that has to do with the ions. It is found in the solid, liquid, and gas form, the only substance that is naturally found on Earth like that. It has these extremely nourishing qualities. It's what nourishes us. And it also can be extremely destructive, extremely beautiful, extremely amazing. So Allie, I want to get a picture of you in Baja doing this. And so, right, we can say that is you there in Baja, or that's me when I go to visit her. Or I actually should put a picture of my snow gnomes. I made snow gnomes. But I love this picture. I actually had snow here at my mom's the first week we were here. So you're all jealous, I'm sure. So what's so special about water? So I alluded to this in our first lecture last night, Monday night. Well, it's extremely simple. It's just 3 atoms, an oxygen with 2 hydrogens. In fact, water was always considered one of the original elements, right? We had earth, air, and water, and then fire to transform them. And then actually the 5th element that most people leave out because they don't understand it is the essence of everything, which is the ether, which is our spirit, our soul. Anyway, the vibrations. So it is very shapely. It's that bent angle of 104.5 degrees. And the oxygen's greed, it wants the electrons for itself, so it's always pulling like a magnet. So, or like the polar bears. So what is polarity? It is a magnetic pull. And so water has, the oxygens have this dipole moment of the negativity. And so it is attracted to the positivity of the hydrogen. So that the dots are hydrogen bonds. We are going to see these halfway through the term when we get into the oxygens. But right now we're going to be with hydrocarbons. But this lab that you're doing, you're going to be exploring if things do mix with water, they would be polar. They have to have something that has a positive and a negative area, so that has an attraction to water. And so that's actually a wonderful cartoon that somebody made of the oxygen always pooling, and the hydrogen doesn't really care. They're like, yeah. So water is mistakenly called the universal solvent because it likes polar, does not like non-polar. What is a solvent? It is the part of a solution doing the dissolving. It is the part dissolving the other part. So the other part, I know all these bonus questions should be doing this live. Oh, it would be the solute, of course. All right, so there you go. Not the best picture, probably not made by a chemist. So typically, covalent bonds are shown as a line, and hydrogen bonds are not actually a bond. Hydrogen bonds are actually an attraction. They're just an attraction. And so they're shown with dots, as I showed the previous slide had that. And so it's an attraction, it's magnetic, but you can pull the magnets apart. So it is like holding hands. And so if we get enough jiggles and giggles, your hands are not going to keep holding. So if we in class we're all holding hands, we got enough jiggles and giggles, we would let go. But the covalent bond of the water molecule is like your arms attached to by your shoulder to your torso. And no matter how much giggling and jiggling you do, no matter how many balls you throw and jumping jacks you do, your arms are not going to come off. But if we did jumping jacks all trying to hold hands, oh, I guarantee you those hydrogen bonds would come apart. So maybe that could be my bonus on here. Come up with your own analogy of the hydrogen bond. What is the attractive, the giggles and jiggles? Or you can just giggle and jiggle along. Is water really the universal solvent? No, this is our next slideshow we'll be talking about for next week, and the issues with plastic and stuff. And so what determines solubility, again, is if you're polar or you're not polar. And so there is this little mantra that's called like likes like. So polar likes polar, non-polar likes non-polar. And they tend not to mix. And you can actually, so there's a question that I started with, are you hydrophobic? There's actually some, we're going to actually look at this video that these guys made. So these are examples. The one on the leaf, it's not actually hydrophobia on this leaf. It's actually that leaves have these, it's microscopic hairs. And those microscopic hairs keep the water droplet from actually absorbing into the leaf. So of course water absorbs into the ground and in through the roots and stuff. But we're gonna go ahead and watch this video. Let's see. Yes. Oh, no.
That's so cool. I can literally watch that one.
Yeah, I know, it's awesome.
Hello there and welcome to this extremely scientific episode of the Slow Mo Guys. We're in a lab.
Yeah, for once, right?
For once, our lab coast makes sense.
Yeah.
GE actually flew us all the way to New York to their labs, which is awesome.
Interrupted my holiday and everything.
Yeah, they want us to film a bunch of their technologies, so we're going to start with this video. We've also done 2 other videos on GE's channel, so be sure to check those out. Check those out.
Yeah, so this video we've got some super hydrophobic material. It's man-made. It acts similar to a lotus leaf, so if you want to squirt some water in that, show. So yeah, the water runs off. Yeah, and that's hydrophobic material. This one here is man-made, and we're going to test that with some food colour and water, and get that in slow-mo. see how it looks.
The way it works in nature is that there's actually tiny nanoscopic hairs on the plant which trap a layer of air, and that causes the water just not to be able to penetrate. There's basically just bouncing off air that are trapped.
Yeah, and this is the man-made version.
So we're going to take the Phantom and we're going to take a macro lens and get some super close-up shots of the way water reacts on a super hydrophobic surface. Science.
Wait a minute, I'm just pouring out some food colouring into this container here. We're going to pour it onto the surface all at the same time, hopefully.
Get a nice collision, yeah?
Get a nice collision, sort of splooshing, if you like.
Yeah.
Good word.
That is the technical term.
Yeah, I believe so.
So we've got red and blue.
Red and blue. Hopefully we'll merge and we'll get some full shots. How much do you want done?
Let's just first just do it.
Cool. Okay. 3, 2, 1.
Whoa.
Wasn't that
Honestly,
cool?
look at that! I've seen robots with less timing than that.
That's ridiculous. Literally perfect.
So you see the water
I like how it
drop.
sort of just looks like a flower. It spreads out completely and
Yeah.
it just bounces off.
So weird.
It's really cool.
Here's your bonus question. Why does the water keep making these spheres as it bounces off? Something you learned in Chem 104. And I alluded to in this video. So you have to explain it.
Alright, so now we're going to try that again, but backlight it so we can see through the liquid.
3, 2, 1, shot.
But it's all like a second video. They slow-mo it.
So another thing that happens is that iron filings in water, when the magnet goes up to them, it's very easy to differentiate the iron filings from the liquid. If the iron filings have been shaved down to a nanoscopic scale, you basically get metallic liquid.
Like Terminator 2, basically.
It looks like
That's the best way to explain
the T1000.
It is so cool. Okay, so here is the ferrous liquid. So it's got the nano-sized iron filings and iron particles in there. Okay, and this is a magnet. You're going to place the magnet down the test tube like this. Okay, and then lift up the liquid towards the magnet and watch as it
Give it a go.
It gets attracted.
See how it like indents before? It like pushes down and then shoots up. And you end up with basically a magnetic ball.
That is really cool. And look,
So good.
it even sort of attracts to other bits of metal as well.
Yeah.
You can see how that works there. Yeah?
Yeah, and keep the plate angled slightly towards the camera, not away.
Okay. Ready?
Yeah. Whoa. Alright, it's good.
So I wanted to show this part also because it's really the idea behind polarity. It is a magnetic attraction of the positive and negative, the north and south. So it's a similar, very much the same idea. This is actually iron that's so nanoscopically sized and it is then in the water, and so it makes the water this ferromagnetic, gives it ferromagnetic properties. And again, this video is from 4 or 5 years ago, and so anyway.
I just love the way that it...
Sorry.
There's no need for that.
I'm sorry.
This was literally brand new. I'm actually
That's
over.
literally been in use for about 30 years. Well, I hope you enjoyed that video. Can't really go wrong with liquids, they always look good. So be sure to follow us on Twitter and also check out the 2 videos we made for GE's channel.
I have to go next.
One is called MEMS.
His lab coat was not hydrophobic, but there are actually sprays that people put on their clothes, and so their clothes don't get wet. So that was hydrophobic. Hydrophilic is loving water, like a mermaid, and I apologize. So hydrophilic is water loving, hydrophobic is water fearing. Now this is interesting. This is a beautiful picture. So amino acids, nitrogens also have a pooling. And then we have 2 oxygens. So amino acids, most of them, they're going to be hydrophilic. Now, in this molecule, so we talked about every corner is a carbon. So even though we have the oxygens, whoops, let's go back. Even though we had the oxygens in testosterone, there's not enough oxygens compared to all the carbon, and so it doesn't mix with water. And so our next question was where I was trying to find examples that we could walk through as a hydrophobic or hydrophilic, and I ran into this new word. And then apparently I made up a new word last night because I called it amphiphilic, so loving everything. This is how they spelled it on this question, is amphiphilic. So it's yeah, which amuses me. So 1 and 4 are only carbons and hydrogens. In fact, we'll probably run into a question where you're going to have to see if you can count all those carbons and then figure out how many hydrogens there would have to be. We'll get to that over the next 2 weeks. That would be cool. But they are only carbons and hydrogens. Even number 1, though, even though it has that OH, it's just way too big. That is actually cholesterol. It is hydrophobic. Be careful on Google. Google gives a lot of wrong answers because anybody can post. And oxygen does not make something amphiphilic. It has to have number 2 is the one that would be both. So see all this, these negatives and positives make something extremely hydrophilic. Loves it. And we have lots of oxygens in there. But on number 2, it's this piece up at the top right where it says C6H13. And that, oh, there's my laser, if I can get it to work. This piece here is the 16 carbons. That part is not going to like water. That's going to make it have this hydrophobic part. So this part down here with the positives and negatives and the oxygens is very hydrophilic. And this part up here is very hydrophobic. And so when it gets to be both, we have the word emulsifier, like soap, as Emma had said last night. But the word magically has appeared is going to have the amphi something. We can all make up our own ending for it. Number 3, it's not enough oxygens for the size of these carbons. So number 3 is hydrophobic. 1, 3, and 4 are hydrophobic. Again, even though this has a lot of carbons, we got lots of oxygens. We have nitrogen, we have phosphorus, and we have the ionic part to it. All right. So let's try the next slide. So I have this there because it comes from the word amphibian. So amphibians, amphi means they could live on land or on sea. I picked the frogs because I was on a walk with my mom, and I was like, you know, in the apocalypse, in Revelations, there's the 7 signs of the apocalypse, and I was trying to think of it, and all of a sudden my mom said frogs. That apparently there was an invasion of frogs, and so I haven't had a chance to go and look at that part, but I'm waiting for that. Wouldn't that be fun? Just have all these frogs, all these wonderful frogs show up. So looking at this picture, so you can stop me. You guys all have the ability to freeze me. And, well, maybe I'll put this question on the lab and see how you do. So try the answer. We'll go through it here. You're going to have to explain why. Number 1 is the frog. And again, we'll see if I can get my laser to work, is we have all these, this very hydrophilic middle part. We have this positive. When you get positives and negatives, and we have a negative, that makes it very hydrophilic. But on each side, we have these long carbon chains, which makes it very hydrophobic. This is a phospholipid. And so this one is both hydrophobic and hydrophilic, so it gets this other name. On number 2, that is extremely hydrophilic. There's so many oxygens. Every carbon has an oxygen. And then on number 3 is the amphi also. So we have the one end, the left side, and yeah, we'll go back. I was trying to get my laser, and your teacher's not actually very good at that. But on all those carbons and oxygens, those are hydrophobic. I'm sorry, that's hydrophilic. But then on the right side, we have these C10H21s, and so that's hydrophobic. So that makes it an emulsifier. It has both parts, and same with number 4. So 1, 3, and 4 are actually amphiphilic. Trying to say these words. All right. So water is everywhere. This is I'm going to go through what the 2 things you have to do. That was one part of your lab. I'm going to have that page there. Just been inspired for what I have to do. But water is everywhere. Every organism on this planet needs water for survival. Humans are the only living being that actually wastes this precious molecule and deliberately pollutes it. So even if you might be unconsciously doing it, we all do. All is forgiven though, as we learn and move on. So how much of the Earth's water is suitable for drinking? Oh, it's definitely not 90. It's not 50. It is, I'm pretty sure, the 1%. Now this was interesting. 71% of the global population actually has safe, managed drinking water. That's like you and me at the top. We have safe drinking water. Now, 10 years ago, Joey and I were in Nepal. Safe drinking water, as defined, I think this is the World Health Organization, is located on premises, available when needed, and free. I'm sorry. Oh, I have it covered up. So it is Southeast Asia and Africa that are the places where they don't have access to clean water. And so Nepal is on there. Joey and I were in Nepal, and I can tell you it is, so the other 29%, well, 2 billion people. It's significant, right? 2 billion people. We all take it for granted, the water we have. And in Gresham, my gosh, we have the Bull Run Reservoir. 2 billion people use drinking water sources that are contaminated with feces. Yeah, and then you get sick. Been there, done that. 89% of the global population. I don't remember where I was going with that. Anyway, it's a basic service, is an improved drinking water source that comes within 30-minute walk. So even though we say 71% of the population has safe water, a lot of these people have to walk every day 30 minutes each way to get their water. Now, this is a part of your lab, and you can use one of the things I talk about and look into it. These were some things for me, because we all know the problem. This is a problem, that our water is not always safe. That you need to find something that is a solution. There's not one solution, but there's many. And one of them is the Dew Bank bottle. So if you want to look into this one, you can. And we're not talking about Mountain Dew. If you drink Mountain Dew, you should give it up. We're talking about this, and it's inspired from this beetle. So it's called the fog basking beetle, captures water from the night air. So your goal is you're going to look into some way we can help with water, a very innovative way. And you're going to write a page about it. We're going to be doing this next week about, I think it's alternative fuel sources or global warming. What are some of the solutions? So you'll be looking into something there. We'll talk about that next. But anyway, so what happens with this beetle is when the fog comes in every morning, we're all used to that, it sticks to its rear end. It sticks its rear end in the air and it catches the water. And then it flows into its mouth. That's how it gets water. These things are living in desert areas. Isn't that cool? So morning dew condenses and it runs down. And so somebody studied this beetle. There's the actual picture of the beetle letting the water run off of its back, its little hydrophobic back. And they created something like that. So we put it outside here in the desert, and it's collecting the fog in the morning, and it collects clean water for people to drink. Isn't that cool? It'd be really cool if somebody wanted to look into that more, and maybe every one of you will. This is another one. So they're called biomimetic interfaces, a synthetic surface with 2 layers. One, the top is hydrophilic. The top, why would the top? And the bottom is hydrophobic. So it makes water droplets detach as soon as they get large enough. That's pretty cool. There you go. This is what they're doing with those. And so they're able to collect water. So they use the material to coat the roofs of houses and buildings, and it channels the collected condensed water from fog and dew into a tank. So we can water the land and grow our own food. 6.5-foot collector can collect 10 liters in 24 hours, which is plenty. Isn't that cool? Look into that. And there's another picture. Again, this is from 4 years ago. Yeah. So there's probably other ones, new ones. And there's also spider web water collectors. So this was from a Nature article, and silk fibers change their structure when they're wet, forming a hydrophilic spindle knot. And so these are giant spider webs that they have created, and they catch the fog, even larger ones. How cool is this? That is so cool. So what about the ocean water, right? We all know that there's all this water out there, but there's too much salt. And if we drink salt water, we actually lose more water. Well, it turns out nature already had a solution, and those are mangroves, which with the increase in communities along coast, a lot of these were destroyed. But desalination of seawater is very expensive, requires a huge amount of energy. It's actually going to be our biggest energy source or use. Mangrove trees filter the salt out of the seawater through special membranes. So a lot of these were killed off, but they have these huge root systems. And so it's been studying them. The seagull is there because seagulls actually have these glands, these nasal glands that expel salt. So when they drink the water, their nose actually gets rid of salt. And so I'm not saying for us to have this device that we wear, this beak and stuff, but that we can learn from that. So maybe that inspires you for something to write about. There's also the solar powered desalination. So it could be that you want to read about collecting water, innovative ways to collect water, innovative ways to desalinate. Camels, when a camel breathes out moist air, its nostrils actually suck in, trapping the moisture. This is an idea that astronauts took from. Their pee was cleaned out in the water, because then they're drinking water, because when they're in the spaceship, yeah, in case you never knew that. They also suck in water from the humid night air. So there is something called the Sierra Forest Project, which is new ways to cultivate desert land to grow food crops. And so it's seawater greenhouses. So you could look into that. Yeah, which is, all right, just trying to spark something here, or you can just say innovation for water treatment, innovation for water collection, something. I don't want to know the problem. I want to know a solution. So you can have one sentence about, well, this is an issue, but this is what we're doing because we can, and we are. That's why we're humans, is to take care of this planet. So if you could ask nature anything, what would you ask? Animals and plants have a very intrinsic ability to monitor and self-regulate. And so do we. We've just removed ourselves from this cycle. We only pay attention when we experience that heart attack moment, that moment when we say, which is really what we're in right now. We're all going, oh my goodness. These are all called, a lot of the stuff is bio-inspiration. So you can Google that word. And it's ways that nature has figured out how to manage different resources. So right now we're looking at water, because the topic is hydrophilic. So bio-inspiration. So these, the suits like Michael Phelps wore and all those swimmers, which was the shark skin, right? The gecko foot is a bio-inspiration. The San Diego Zoo says by 2025, $300 billion. So it's not about the money. It's about all of us having. This is actually really cool to me. And so that a Toronto-based wind power company has designed turbine blades based on the tubercles on the fins of the humpback whale. And so on the left, the picture is the fin of the whale, and the right picture at the top is actually the turbine blades. The bumps reduce the drag, enabling the blades to turn at very low wind speeds. How cool is that? That's what we're seeing. It's already there. It's already in use. So you're going to have some questions to answer about hydrophilic, hydrophobic, looking at those molecules that we went over. You're going to have to write a page about some innovation to help us to have water, safe water for everybody on this planet, or desalination or something. Just a page about it. You can write two. Make sure you put your reference in there. And then you're going to also do a little kitchen chemistry experiment. And so you're going to pick, it could be vinegar. You're going to pick 7 liquids. You're going to have water plus 7 more. So it could be pickle juice. It could be, I don't know, alcohol, oil, vinegar. I have a whole list. Whatever you have, it could be salad dressing, high fructose corn syrup, total crap. So why not use an experiment? It could be fingernail polish remover. And you're going to figure out which ones will mix with water. So you're going to have like 7 glasses. So little Dixie cups work great. Or you can have, if you have like, I don't know, Gatorade, you can do, see what is polar. Safety first. You are going to have to take a picture of yourself doing your experiment. So a selfie. Now, have fun. Make your selfie fun so your teacher laughs. That's always good to keep your teacher happy. If you have goggles or safety glasses, you're supposed to be safe. You should be wearing them. I do ask, can we limit ourselves to no more than 5 pictures? Some of you had a lot of fun last term, and I would get like 20 pictures, and you can do 20 pictures because Christy told me the hint, which is how I'm doing it, which is you put it into a PowerPoint, and you can embed the pictures into actually your document. So some of you figured out how to do that, and so have fun. Make sure you take good notes, that you write it down, because you're also then going to pick one of your things, so like say oil, and then you're going to make that the solvent, and then you're going to try your 7 substances also in that. And just make sure you clean up. If you never saw that joke, caution wet floor. So clean up your kitchen afterwards. And that's it. So have fun, and it's due on Saturday. All right, bye-bye. See you soon.